I'll stop sharing and then hand over to Richard.
Okay, thanks a lot, and thanks to the FSC for inviting me, and thanks for coming along. So basically this is a sort of introduction to passive acoustic monitoring. I discuss exactly what that is, why it's useful, and how we do it. So let's start off by defining what we mean by that. One of these doesn't work, that's better. Okay, so recording sound is a passive activity. You're not disturbing anything directly by it, it just gathers sound that's coming in. So it's non-invasive, but here we're sort of focusing on autonomous collection of sound. So that is without the presence of a human operator or observer, and you're using technology to record the sound, so it keeps disturbance to a minimum. And acoustic, we're obviously referring to sound. Sound's basically classified according to the range of human hearing. So audible sounds are between 20 Hertz and 20 kilohertz. Ultrasonic sounds are those above 20 kilohertz, and infrasonic sounds are those below 20 Hertz. So those are the three sound categories, but we'll come back to those later. And monitoring, because basically it's more on a long-term data collection. You know, not just for an hour or two. If you're going to actually bother to put sound recorders up in the trees, then you want to leave them there for a while. So essentially it's just collecting sound passively over a longer period of time, which is passive acoustic monitoring. So it's a fairly recent field, since about 2010, but you can see this is a graph of annual citations that are being published in academic journals that reference passive acoustic monitoring, and there's been a pretty drastic increase in the interest in this field since 2010. As you can see, it's still going up. So why would we want to monitor sound? Well, sound is really important for a lot of species for different things, such as territory marking, mate selection, alarm and social calls, feeding and navigation. So if we look at some of the species or species groups that you monitor with sound, I mean, birds are quite an obvious choice. Songbirds, particularly passerines. Bats are also really good for monitoring sound. These are micro bats, actually, echolocating bats, because fruit bats don't use ultrasonic sounds, but for navigation. But those that do, because they're always echolocating as they move around the habitat, they're really good to pick up, and you can identify them. And then we've also got other terrestrial mammals, obviously whale calls, and has been monitored for quite some time. Orthoptera, which is basically crickets, katydids and grasshoppers, and cicadas, so inverts make sounds that you can monitor. Frogs and toads, not so much in this country, but really big in Australia and South America, monitoring frogs and toads using acoustics. There's a lot more people now looking into freshwater sounds. We've found out that water beetles and various other freshwater inverts make distinctive sounds that you can record. And one that you might not immediately think of is fish. Fish make sounds that we can record and potentially identify species. So you can see there's a really large and varied group of different taxa that we can study with sound. So it's very flexible and useful. So recording animal sounds isn't new in itself. We've had the field of bioacoustics, but that's traditionally been focused on physiology, communication and behavior between a specific target species. Usually it's been limited in scale, so people have just gone out with a parabolic mic or chased around whatever species they were interested in recording, or kept them in a lab and recorded them and studied how they use sound for communication. But the use of passive acoustic monitor has basically expanded the scope of bioacoustic studies, and now we sort of have everything under this umbrella of ecoacoustics, where basically we look at sound as a source of ecological information, potentially at the population, community and ecosystem level, and we can also study it over large and temporal spatial scales. And what's called a soundscape approach is part of this. So what do we mean by a soundscape? Well, a soundscape is simply all the sounds that emanate from a landscape. And the way we sort of categorize these is three quite broad and intuitive categories. Biophony, which is the sound of any animals. So that's songs, calls, echolocation, stridulation of the inverts, any sound that's produced by animals, non-human animals. Geophony is abiotic sound, so you might have rain, wind, and anthrophony is the sounds made by humans and their machinery, so traffic, noise, aeroplanes, gunshots, chainsaws, machinery, that kind of thing. So, as this is about sound, let's see if this works, and we'll have a little listen to a soundscape. So this is about half a minute of Sumatra rainforest. Hopefully you can all hear it. But just a little thing, don't bother in the chat, but just to yourself, have a listen to this soundscape and try and see how many different species that you can hear within it. And we'll see if this works. Okay, so hopefully at least some people heard that, yes? But for anybody who did hear it, this is a spectrogram of a section of a longer section of that sound. It's only about 2.5 or 3 minutes, and that was this first part here. So first of all, just to introduce spectrograms, listening to sound is a real-time activity. So if you wanted to listen to 10 minutes of sound, it's going to take you 10 minutes. And so one way that we work with long sections of sounds is to view them as an image. And for anyone who's not familiar with spectrograms, you've got time along the x-axis and frequency along the y-axis, or up the y-axis there. And the intensity of the sound is basically represented by the brightness in the image. So you can see that these white dots at the bottom are quite loud, whereas those darker areas at the top is quiet. And what's useful about this is, as I say, it allows you to look at longer periods of sound without listening to them in real time. And also things become a bit more obvious, but it also allows us to see frequencies in the ultrasonic that we don't hear, for example, for bats. So hopefully you all heard the orangutan, or at least thought it was some kind of primate at the beginning, and then there was various different birds there and maybe the chirping of insects. You must have really good hearing if you heard any bats in there. But you can just see from this image, it's 2.5 minutes long, and you can already see there's half a dozen different species of birds in there, a mammal, a couple of species of insects, some bats, and you're getting a huge amount of information about the environment there in just a very short survey time. And another interesting thing, if you look at this, that it's quite well organized. Everything seems to be very well structured and partitioned, and there's a reason for that, which we call the acoustic niche hypothesis. Now, this is based on the concept that, similar to landscape ecology, where different species have to share resources and they each occupy a habitat niche based on their foraging and nesting or habitat preferences. It's a similar situation in the sound environment, where sound's a finite resource, basically limited by hours in the day, or hours in the day that you're active as a species, and the frequency over which you communicate. And a similar example is like with radio stations. So because you don't want to be broadcasting and competing with another radio stations are on different frequency, and they also transmit their programs at different times of day rather than putting them all simultaneously. So in the same way, we kind of expect that over time, to avoid competition and overlap, the different species will occupy different acoustic niches. And you can kind of see that this is a theoretical image, obviously, but when you look at the soundscape, which is an actual recording, you can see that there's some quite similarities there in the way that things are blocked out. So, and here's some real life examples, and basically this is frequency niche partitioning of frogs at the top, and then frequency and temporal partitioning of sounds by fish in South Africa at the bottom. So you can see there that the different species within the same habitat have sort of separated into the different frequencies that they use to minimize overlap at different times of day to a certain degree. Okay, so that's great, but why is it any useful? Well, following on from that, the idea that longer established undisturbed habitats should demonstrate more complex and diverse niche partitioning. And whereas disturbed habitats should exhibit gaps where species that were occupied these acoustic niches have disappeared, gone extinct, moved away, and potentially also you could highlight the presence of invasive species in there if you recorded them. So we'll try a bit of sound, hopefully. Oops, sorry, I skipped that. Let's try that. So the first half of that sound was basically this meadow before, or forest, before selective logging had taken place. And then the second part of the recording was after this logging. And the interesting thing is that visually the forest looked almost the same. So you might look at it and think that it hadn't really made any difference. But when you listen to the soundscape as it was recorded before this took place and afterwards, you can hear a real difference in how many species that were present originally, and then just a solitary woodpecker pretty much in the second one. So this before and after is a good way of assessing the impact of various habitat management practices and anthropogenic activity has on soundscapes and thus the biodiversity that's there. So we'll have a look at another example. And basically this is a coral reef, and on the left hand you've got a reasonably healthy reef, and on the right you've got a bleached reef that's pretty much devoid of life. So the first part of the recording will be the left, and then the second will be the right. See there that in the first half, hopefully you heard like a kind of sound like Rice Krispies, that snap, crackle and pop, which is basically fish gnawing on coral and shrimp and various things like that. And then in the bleached coral reef where there was very little life, you could hear how silent that was. And so again, monitoring sound as an ecosystem approach gives us this idea of the general health of an ecosystem. So it's really useful for that. Okay, so how do we actually perform acoustic analysis? So don't worry if this is a bit overwhelming. I'm going to work through each, this is a kind of overview, and we'll work through each part of this in stages. So the first part will be data capture. Obviously, if you want to analyze sound, you've got to go and record it. And as I mentioned earlier, it's pretty much classified as audible, which is the range of human hearing there, 20 hertz to 20 kilohertz, although that's a typical range. People will vary. Anything above that is ultrasonic, and anything below that is infrasonic. And the frequency ranges that you'll choose to monitor will be dependent on the species that you're looking into. So ultrasonics, typically bats, most Orthoptera, or at least some Orthoptera, echolocating cetaceans. Anything in the audible range you'll probably be familiar with, because you'll have already heard it at some point. Obviously some things like fish and snapping shrimp you won't have. And infrasonic, not so much going on there, but elephants use infrasonic, and baleen whales juveniles. So it's larger species. Generally, the rule of thumb is that the larger something is, the lower frequencies it produces. So depending on which of those groups or species you wanted to monitor, you would decide what frequencies you wanted to monitor and get the appropriate microphones and equipment. So just some silly pictures, but basically this emphasizes the point that a lot of the recent interest in acoustic monitoring has been because we've actually finally been able to get compact, reliable and affordable digital sound recording devices. And until recently, again, as I said, about pre-2010, some people were still using the old C90 tape recorders and going out and carrying them to field work. But now we've got much better tools for this job, which has helped sort of influence the growth of it. So you've got portable and static recorders. So portable devices are such as this Zoom H1N, which is a sort of handheld lecture theatre recorder. I've got one of these. They're pretty useful. You can carry them around, and portable bat recorders. So these are useful tools for point counts and transect surveys. And basically you create a permanent record so you can reevaluate it or get someone to check it for you. It's useful if you're doing bird point counts a lot to take one of these, and as well as counting, just take an audio record. So because you're trying to focus on one bird and you might miss another that's singing in the background, or you might hear one that you can't identify. And it's been pretty much shown that you can increase the number of species that you detect if you do a manual point count in combination with an audio record. And for species such as bats, you don't need a permit because they're a protected species. So if you wanted to go and start digging around in roosts or netting them, then you need a special permit for that. But as this is a completely passive technique, you don't need a permit to survey species such as that. The only problem is with portable devices is that obviously you need to carry them around. So you will be there. And so it's not entirely passive because some species might avoid you or be more hesitant about coming out and showing themselves because of that. And they're relatively short duration, and as you can only be in one place at a time, you can only do one location at a time. And for these reasons, we've seen an increase in use of what we call autonomous recording units. There's various acronyms for these, but I'm calling them ARUs in this. So just have a quick look inside one of these, and these are some I built when I started doing my research project. And inside is just basically a microphone for the frequencies that you're interested in. I wanted to study bats and birds, so you've got an ultrasonic MEMS microphone in there and a little sort of EM172 audible microphone capsule, which is really good quality, very small, quite cheap. And then you have to have some sort of capture, storage and processing electronics in there to record your sounds and decide when to record your sounds, and a power supply. And then you basically put it all in a nice waterproof box, non-destructively attach it to the side of the tree and hope nobody steals it or throws rocks at it or whatever. And you can put some optional extras in there. And internal clocks pretty much essential these days, because if you wanted to do schedule recording, so you only wanted to record at night or during the daytime, or if you wanted to record 1 minute in every 10, which is what we call a sampling schedule, and also because it time stamps your data so you know what date and time the recording took place. But some people are also now putting solar panels on them so you don't need batteries, so they can stay in the field a lot longer, and Wi-Fi and 3G transmitters, so instead of recording your data to data cards and having to go around and swap the cards, you can just transmit it over the network to a server somewhere, and then you can just look at it. So these are some commercial recording devices. So the Wildlife Acoustics has been around for quite some time now, and these are really sort of ready to use out of the box. They're quite simple to set up. They use regular batteries. They've got a very good long field life and come with mics inbuilt, but they're quite expensive. If you can afford them, great, but especially if you're doing a large scale deployment where you're using several sites. But because of the interest in this, and as with any competitive market, the prices have been gradually coming down, and you can see in the bottom that Cornell, which is a university in America. It's basically very big on ornithology. They went out and developed their own one and made it available to anyone who wants to buy it now for $250. And additionally, scientists and researchers have been coming up with their own answers to these, their own versions of these acoustic recording devices. So here's one at the top, which has taken one of those sort of handheld portable devices, plugged in a battery pack to it, stuck in a waterproof case, and as their own solution to a longer term way of monitoring. Then you've got consumer electronics such as the Raspberry Pi and the Arduino, and people have written custom code to turn those into acoustic monitoring devices. And then finally, Audio Moth, which has now kind of become a pretty much de facto device for many people because it's only about $50 and you can order it via group gets. Just takes a couple of AA batteries, you put it in a Ziploc bag and attach it to a tree. And if you lose a couple, it doesn't really matter because it hasn't cost you nearly £1,000 or whatever. So that's custom design electronics and code, so it's got longer field life and all that kind of thing. So once you've been out there, you put your recording devices up and you've left them in the field and you've recorded, then you need to actually look at the data you've got and try some form of analysis. So this could be the form of manual identification, automated identification, acoustic indices, which I'll explain in more detail, and anthropogenic sources. So the first thing to bear in mind about acoustic monitoring is it creates big data. So 24 hours of an uncompressed wave at 44 kilohertz, that's monitoring up to 22 kilohertz, because 44 is the sampling rate. That's 7 gigabytes. And if you had 10 sites with one recorder in each and you recorded for 1 month, you would generate 2.1 terabytes of data. So that's 2,000 gigabytes, yeah, pretty much. So you need somewhere to store this. You need to make sure you've got backup copies. You need to organize it. And then on top of that, it's the time that it's going to take you to analyze that, because that's a lot of data. If you imagine trying to listen to 10 months of continuous 24/7 audio recording, it's just not possible. So you need some way of analyzing this. So the first thing we'll look at is manual identification. So this is nice because it gives you information on specific species. Sometimes it's even possible for some species to identify those to individuals. So someone's published a paper saying you can identify cuckoos as individuals based on their call. I've seen someone else talk about tawny owls as another species you can identify to individual based on differences in calls. So you can even now start getting down to individual level for some species. And any recordings, because you've got a permanent record, can be re-evaluated. So if you're not sure or want to get a second opinion, it's there. The problem is it's slow and intensive work and requires knowledge of the calls. And some species have quite big repertoires. And then also occasionally you're dealing with mimics, so things like drongos, which is a bird in Africa, which mimics various other creatures, and lyrebirds, etc. So we're going to have a go at this, and let's see. We're going to try some manual identification of species now. So here's a spectrogram of a call, and just to have a quick look at the characteristics of this, you can see it's pretty much between 1.5 and 5 kilohertz for the most part. So that's within the range of human hearing. So it's something that you would normally hear. It's also quite a varied pattern. So it goes up and down, different frequencies. And I'm going to mute myself now and we'll have a quick listen. And if you want to type in chat what you think it is, either the group or the species, we'll see how everyone gets on. Did we hear that okay?
Yeah, we've got lots of people saying blackbird in the chat, loads and loads.
Okay.
Everyone's got it.
Okay, great. Yeah, yeah, that was quite an easy one to start with, but well done. I did play this to other people, and they didn't recognise it. Obviously, it's a bird, but they did get blackbird. So great. If you got blackbird, well done. So let's try another one. So this one is between 10 kilohertz and 45 kilohertz. So you're going into the ultrasonic frequency range there. And you can see it's quite a regular, broadband, repetitive call. So let's have a listen to this. And because it's in the ultrasonic, there's a few ways we can listen to ultrasonic calls, because obviously we can't hear it, that frequency range ourselves. So my favorite way is to basically play the recording back at 1/10 speed. So this is 1/10 of the speed that it would normally occur. And by doing that, you basically bring it down into the range of hearing. So I'll mute myself and we'll have a quick listen to that. Okay, any ideas on that one?
Okay, so Mike Carey has said bat, Sam Batman said pip. Oh, hang on, it's going well now. Noctule, agree on bat, noctule. Oh, someone said not a bat, and someone said bat. Too low for pipistrel, isn't it? Noctule, yes.
Okay, so I did accidentally click that a little bit earlier, trying to unmute myself. But yeah, nice to see people actually trying to guess the species there. That's a long-eared bat, a brown long-eared bat. This is quite a quiet bat as far as it goes, quite difficult to record, so I was quite pleased to actually pick those up. I can see why you might think noctule, because they are quite low frequency, but this is more a sort of broadband call, more like a meiosis, I guess, fundamentally. Okay, so here's another one. And again, this, what did I say again? So this one goes from basically about 0.5 kilohertz up to 5.5 kilohertz. So again, it's in the range of human hearing. It's quite a complex call, a little bit different to anything we've seen, because you've got these harmonics. So I'll mute myself if I can and have a listen. Okay, what might that be?
Okay, so in the chat we've got gull, terns, marine mammals, seals, gulls being weird, frogs, shearwater, dolphin.
Okay, I'd never thought of gulls actually. It does sound a bit gull-like. It's not. I should mention as well that these are all recordings that I made myself, so I haven't done any aquatic stuff. But let's try and feel. So that was actually deer in Richmond Park, and I've never heard deer make that sound before. You obviously might hear the male red deer kind of bellowing around rutting time, but this was out of rutting season, and after talking to a few people who know more about deer than me, we reckon it was probably red deer. It could potentially have been fallow, but it sounded more like red. And also probably there was like Bambi in there, so like some young deer. So potentially also listening to sounds gives us some info on breeding success. When the young make a different sound to the adults, you can kind of tell if they've been breeding or not. So that was quite a nice one. We picked up some deer. Okay, a couple more. Oops. Okay. Sorry, I jumped ahead there. Let me. It's a bit of a pain having to mute and unmute my mic every time. So here we've got a very low frequency sound. Some of you might have heard already. But basically it starts off a very low frequency, goes up to a couple of kilohertz. So again, it's audible, but it's a very short impulse, very loud kind of short duration sound. And we'll just have a quick listen to that. I think pretty much everyone should have got what that was.
Yeah, well, we've got gunshot, cannon, thunder, but yeah, gun.
Yeah, exactly. Yeah, it was a gunshot. And so Homo sapiens basically was that one. But the interesting thing with gunshots, and similarly with chainsaws and lorries and things like that, is we can use them to assess anthropogenic impacts. So gunshots is used quite frequently now to estimate hunting pressure. If you stick out a load of recorders in an area where you know people are hunting and you see how many gunshots we're recording, it gives you some idea of how much hunting's going on. So you can apply this for quite a few different things for conservation as well as just for monitoring species. And one last one. Okay, so again, this is 25 to 45 kilohertz, so it's in the ultrasonic. So again, this is at 1/10 speed, and hopefully this will play. It's quite short.
Okay, we've
Any
got
ideas?
people saying cricket in the chat. Ricardo, any other suggestions? Bush cricket.
Well done. Whoever said bush cricket, I guess they've done some bat detecting before. Because one of the things that anybody who does bat surveys around August will probably know is that you get loads of these on your bat detector. They can literally fill up a bat detector with cricket noises. So they used to be the bane of bat detector people, but now we're kind of trying to look at it constructively and as an opportunity that when you put out a bat detector, you can assess cricket populations as well as bats. So it's a dual purpose, and there's quite a few people now working on this and looking at identifying different crickets by the stridulation. So that's the stridulation when the cricket's basically rubbing the spurs on its legs together to make that clicking sound, a bit like when you run your thumb along the edge of a comb. Okay, so now you get some idea how we do manual identification, and those were just a few examples across the board of various species that you can start to identify by the sounds that they make. So now we're looking at automated identification. And when you've got terabytes of acoustic data, it's great to be able to look through it manually and pick out every species you want, but realistically, you just don't have the time. So people have been trying to develop faster approaches to automatically do this identification thing, both supervised and unsupervised. One benefit is it's left subjective. If you let the computer decide what sound is what, when people are actually identifying them manually, such as people doing bird point counts, some people have better expertise in some species than they do in others. So they might overcount a particular species because they recognize that, but a call that they don't recognize for a species, they might not be less likely to pick it up. So when you process everything automatically, it will just go through it in an unbiased way, but that doesn't mean it's infallible by any means. You've usually got to train and validate these software and set them up in some way. They're prone to the usual sort of problems with acoustic analysis, that you get noise signal overlap and degradation. If you're going to train it, you'll need a reference library, and they're pretty limited at the moment. There's some good ones. Xeno Canto is really good for anybody who likes bird calls. There's just thousands of bird calls on there, all different species, really well organized. And there's a nice forum if you want to try and get a mystery call identified, where people sort of chip in with their ideas and give you a reference. Are quite helpful. But that's kind of quite a unique sort of example. I know some other people are setting them up for inverts, and I don't know if we've got one for bats. I've never seen one. And automated identification is better for some taxa than others at the moment. I mean, bats, it's quite good because, well, UK bats at least, because we've only got 18 species. They're all, for the most part, quite distinctive. There are a few that are difficult to separate, but you can at least get them to genus, if not to species. Whereas birds, it's still difficult because you've got some birds like great tits, which have got a repertoire of over 50 or 60 songs. And then you've got to train it for all of those songs if you want to pick them up all the time. We've got so many different birds. So we'll have a look at some example of automated identification software. So this is Kaleidoscope Pro. This is made by Wildlife Acoustics, who made the SM4 that we looked at earlier. So basically what this does is you throw it at a load of sounds, it goes through them all, and it does something called clustering, where it looks for similar sound events throughout all of your recordings, and it says which ones are most similar to each other. It puts them all together, and then what you can do is review them, and you can build classifiers for these, and you say, yes, I'm looking at that, it looks like a tawny owl call to me, so I'm going to call this one tawny classifier, and then you would go and iteratively improve the performance of this by every time retraining it that you went through your database. So if it picked up a long-eared owl, you would say, no, that's not a tawny, don't look for this pattern anymore, and that way. So that's one method, and that's what we call supervised, because it's not completely automated, you're having some input in it. This is a free package in R, if anyone uses R, called Monitor. And what this is binary pattern matching. So you can see on the left there I've created a couple of templates, again called tawny owl calls, very popular with me. So I've sort of said, these are tawny owls, I know they're tawny owls, this is what the sound wave looks like in a spectrogram, go out and find it. And here you can see on the right, there's an example where it's looking at, I think that's 1 minute of audio, and basically it's picked out 2 calls that it's reasonably satisfied with, match that pattern. So this is quite good, but the problem is you have to build a pattern for every call you want to identify. So it might be feasible for a couple of species, but if you're doing a broad scale ecological assessment, it's a lot of work, and you have to know some coding, but it is free and it's quite good from what I've told of it. And here's one that's fully automated. I like this one. This is called Bat Classify, and it was written for someone as Chris Scott for his PhD, and I use this for most of my, at least preliminary assessment of my bat calls. And you just point it at a directory of files, it goes away, and then it comes back and it gives you this CSV spreadsheet on the right. And what this is you can see across the top, so Barbastelle, Alcathoe, Becksteins, etc. It's got all the different bat species, and then it gives you a confidence rating between 1, very confident, to 0, not confident at all, to say how likely that bat species is within each recording. So you can see on the top row, NSL's like 75% likely that there's one of those in there. That's nocturnal serotonin or Lyslat. And then for PP, which is soprano pipistrelle, so there's a 96% chance. So it's very likely that there's one in there. And the skill with this comes in basically determining what your thresholds are, which are reliable, and validating it. You don't have any input. This has all been pre-trained based on the calls of bats by the person who wrote it. So those are the way that we do automated, some examples of automated identification. So a new approach that we've started using is one called acoustic indices. So you can see there's a lot of information in a soundscape and in a spectrogram. And what an acoustic index does is it looks at the whole soundscape, or at least an area of it that you select, and it analyzes all the sounds together rather than looking at individuals. And this has been tested, well, acoustic indices are now being tested quite a bit, and they found correlations with biodiversity metrics, just as species richness is the one that's been most commonly tested for birds. And the great thing about these is they're fast, they're repeatable, so that if you run one on your computer and I run one on my computer and we use the same settings, we should get the same results for the same audio files. And you can also configure them, and you can also standardize them across different sites and dates. As long as you use the same recording equipment, it's a fairly similar habitat, etc. Then in theory, the recording, the values that you get from acoustic indices should be comparable. But there's variations, there's a lot of acoustic indices, people have been developing these, and there's some variation in what they represent and some misinterpretation of how they're applied, and also includes all the sounds. So it's not just necessarily biophony or the sounds of animals. If there's wind, rain or noise in there, then that's included in the assessment as well, so it can skew your results. And you get no information about which species are present, so it's difficult to sort of dig down sometimes to look at ecological questions. So here's an example of one index. excuse me, the acoustic complexity index. And the theory behind this is that animal calls, as we saw with the blackbird, are more complex than anthropogenic sounds, which typically tend to be pure tone or at least of a constant frequency range. And so this looks at complexity and just to try and simplify this, what it does is it breaks, this is a spectrogram of a dawn chorus, and it breaks the spectrogram down into different boxes, and it will compare the difference between the first box to the box next to it, and it makes a note of the difference, and then it goes through this iteratively until it's done all the boxes, adds them up, and then it comes out with a value. And the idea is that the more complex your soundscape is, as we discussed earlier with the niche hypothesis, is that you will get a higher value from the index. So in practical terms, if we look at our example, here's 1 day's worth of acoustic data, which I've run through with the acoustic complexity index. And you can see there at point A, there's the spectrogram on the right. It's pretty much silent. This is night time. There's nothing going on at this site. And so you get a very, very low value. And you can see that it's pretty flat there at night time across the board. And then at B, which is dawn chorus, you get this huge spike of activity. And so you get a very large ACI value. And C is there kind of, that's dusk chorus pretty much, and that's somewhere in the middle. So you get an intermediate value. And the idea is there, as you can see represented, is that the acoustic complexity is representing the amount of acoustic activity that's going on in the soundscape. So that's acoustic complexity. I don't know how we do for time. Okay, so now that we've done our data capture, our data analysis, we can put all this together. We can use it with traditional surveys, habitat characteristics, or other spatial information to answer or address ecological questions or research questions or conservation issues there on the right. So we'll have a look at some real world kind of case studies of examples of the things that you can, some examples of the things that you can actually study with this. So you can investigate daily and seasonal activity patterns. So on the left, this is basically 5 different bird species. So each of these columns of circles represents a different species, and they're comparing their activity at 5 different sites over 16 days. And already you can kind of see that that 1, 2 down and 2 across is very active for the corvus species compared to the other sites. And at that time of day, the circle basically represents a sort of clock face. So you can see what times of day different species are active. You can see there's some night species in there. And you can also compare sites to see where your species are most active at different sites. On the right is one that we recently published. And basically this is looking at seasonal or nightly activity of bats in the UK. So here you've got this kind of hourglass or half hourglass, which represents sunset and sunrise, which changes with season, obviously. And bat recorders tend to use triggered recordings. So each one of these circles represents a time when the recorder was triggered, and from the time and date stamp metadata, you can then plot that on. And you can see that here around July, you've got a very different pattern which changes through as you go into August, with these peaks in activity just shortly after sunset could potentially represent a commuting route or a roost that's quite near to the recorder, because you've got a large peak in activity as bats emerge and travel to their foraging posts, and then pretty much no activity through the rest of the night. But you can see that you've got sort of nightly and seasonal patterns there, and you can compare these between sites and species. So you can also use it for modeling species distribution and abundance. So on the left here, someone's looking at elephants, and they stuck out these recorders, which are the black spots, and they recorded how many elephant calls they got. And then what they did is sort of interpolation there, where you basically put the values in, use GIS or something like that, and it interpolates the areas where you get the most activity. And you can see there that if you wanted to focus conservation efforts, or preserve a habitat or landscape, it's pretty clearly that bit down the middle diagonally where most of your elephants are spending the time calling and hanging out. The one on the right, this is by Carlos Abrahams, who should be out there somewhere, and he was presenting this in a talk yesterday, which I thought was really interesting, and it's the idea that you can associate the number of vocalizations of a species, in this case capercailles, with the number of adults or the number of individuals that are there. And this would be really nice if we can expand this to a lot of species, because at the moment you can't actually tell whether a call is for most species. Some you can, but you can't tell how many individuals are necessarily present, because one blackbird could sound like another blackbird, for example. So this is associating call frequency with number of individuals or abundance. So this one I quite like. So the common pipistrelle was first described in 1774, and for the next 200 odd years, we assumed that it was just one species. There was just one species of pipistrelle until people started developing ultrasonic recording devices, and then in 1999, Gareth Jones and various others noticed that these pipistrelles seemed to be giving different calls, and they suggested that, well, the ones at 45 kilohertz were actually a different species to the ones that were calling at 55 kilohertz, rather than the same pipistrelle calling at two different frequencies. And this was confirmed with DNA tests, and we actually found out that one species is a common pipistrelle, and the other, because it's a slightly higher frequency, I guess, is the soprano pipistrelle. But these species looked practically identical visually. So it's nice that cryptic species like this you can actually identify by the sounds they make a lot easier than by looking them, catching them, etc. So going back to reefs, this is another interesting one. Basically, as we found out earlier, that reefs are noisy. A healthy reef at least is noisy. So what happens if your reef degrades? It's quieter because you've got less individuals, and quieter reefs attract less individuals. And because you've got fewer individuals, the reef's quieter, and quieter reefs attract less individuals. So you end up going around in this kind of feedback loop where the reef gradually degrades over time, because it's getting less and less individuals repopulating it, and because of that it's getting quieter and so on. So very recently, what some people have been trying out to address this is putting speakers out in reefs and playing reef sounds to attract young fish and coral and various things, and it's actually been working. So this is a nice example of how, by studying and understanding how ecosystems use sound, that we can sort of give them a helping hand where necessary and do something positive. And finally, this one is looking at conservation strategies and assessing the effectiveness. So this one on the left is a really good one. You can see there January to May where there were no patrols by wardens, by gamekeepers, that you had a lot of gunshots being registered. There was a lot of hunting going on. And then what they did was they measured how the number of gunshots altered with the number of ranger patrols that they sent out every day. And there, the second column along, you can see that when you have like 15 or so ranger patrols per 100 days, then hunting pressure, or at least shooting, drops by really quite a bit. And then when you have a lower number, then you get a positive effect, but it's not quite as good. And then in the fourth one, to get almost the same sort of result as the second lot, the second column, you could probably get away with 10 days per 100 and you'll get a very similar benefit. And that's good because it means you could assess what is the optimum number of ranger patrols to send out, because when you've got limited resources, you can't send people all over the place all the time. And then on the right, this is just looking at how the removal of Arctic foxes at different islands over time affected the seabird population by monitoring the sounds that the seabirds made. And the one on the right was one that was never invaded by introduced Arctic foxes. And you can see that that's got a much healthier sort of bird population from the sounds that they recorded. And these other columns are looking at how the islands started to rebound from this over time. So that's pretty much it in summary. So passive acoustic monitoring is useful because it's not invasive. You can have continuous monitoring. You don't require line of sight, so you can use it at night time in dense vegetation underwater. Large-scale deployments are possible because you just go and put these boxes out, reduces observer bias. And a nice one is that it's creating a permanent record for comparison. Because if you think about it, we've got photos and maps and pictures of animals from long ago, but no one ever went and recorded what they sounded like. So we don't know what a dodo sounded like, for example, because no one ever got to record it. So what we're doing now is collecting all these sounds, and we've got them as a permanent record that we can use to evaluate long-term changes such as climate change and assess them against things like that. Obviously, disadvantages, you can't use it for anything that doesn't make a sound. You have to maintain the data. It's big data, so it can take a lot of processing. And at the moment, some automated things, species ID is problematic, and acoustic indices still need some work. So I'll just flash you the references there if you want to actually go and look anything up, or you can ask me and I can send it to you. And thanks for listening, and if you want to get in touch and for any reason, there's my email address and I'm on Twitter. So thanks a lot.
Brilliant, thank you, Rick. Bear with me a second, we've had a few questions in the chat. I'm just going to try and figure out where the first one was. Okay, so with automated ID software, how easy is it to allow for variability in calls within a species?
Oh, I mean, that's part of the problem, really. Let me just minimize that. Am I back on screen? Sorry, I need to stop sharing. Did I stop sharing? I can't see.
No, there we go.
Ah,
yeah.
Thanks. Okay, great, that's better. Sorry, what was that variation in?
Hang on. My chat keeps going wild. No, that was a different question. With automated ID software, how easy is it to allow for variability in calls within a species?
It depends what method you're using. Usually it's not quite absolute, so you can get away with some variation, but the problem is when things have a large repertoire anyway. So as I said, with great tits is one that are often mentioned because they have a large repertoire of different songs. It's more the variability in the calls. There will be some variation between individuals, which can be useful because it allows you to identify things to individuals. It depends on the software. I mean, the back classify, for example, is quite good at grouping things, but because bats make pretty similar, their calls do vary depending on the habitat, but it works quite well for them because they're fundamentally quite similar because they use them for the same purpose. So it depends on the species, and I imagine that Orthoptera are quite easy to, there's not a lot of variation because they use a physical method to produce the sound, whereas things like birds and things that vary their calls are going to be harder.
Right. And we've got a question from Dan saying, given advances in data storage and machine learning, where do you think passive acoustic monitoring will be in 5 years' time?
Data storage isn't too bad because I managed to store, I think I ended up with about 14 terabytes, and data storage is something that's always coming down in price because it's driven by consumer electronics. The artificial intelligence is being looked at quite intensively. There's a challenge every year, like from Queen Mary, where they basically say, here's a load of acoustic recordings, we want you to devise a method to program, to sort through this. So it is improving, it's quite a big task. But ultimately where we would like to be is a point where you can just record these sounds, feed them into a program, and it will just give you a list of the different species that are in there and how often they're recorded and things like that. I kind of don't have a crystal ball to say whether that will be in the next 5 years, but it would be great if it would, because that's probably the bottleneck at the moment, because the technology for recording it is quite available and has come along a long way. So if we can progress the identification part to the same degree as we have the recording part, then potentially, yeah, in 5 or so years we could be quite close. But I've been studying this for 5 years now, and during that time, no one's actually come out with something that will fix this problem.
Cool. James, you've got your hand up. Do you want to unmute yourself and ask a question?
Thank you very much, Rich, for the presentation.
Thanks.
If I'm relying only on a smartphone to do a bit of sound recording from nature, do you got any advice, or maybe a microphone that you should use? Anything? Thanks.
Yeah, a smartphone's a really useful tool, because sometimes I've been out and heard something and I've not had a recorder with me, so I've just switched on my smartphone. An example was turtle doves at Nep. So the first time I just happened to be walking, funnily enough, to my recorders. I walked past and I thought, that sounds like a turtle dove, and I never heard one before. So I whipped out my smartphone and recorded it. So it's a nice little tool to have with you. I don't know if the quality is quite up to it if you want to do a detailed analysis. And one of the things I looked at when I started the project was whether I could actually get away with using smartphones as a capture and storage device. You can get some microphones for them, usually those lavalier type microphones, which are the little ones that people clip on there, when they're doing news interviews or filming videos. So some of them take that. Otherwise, as a storage device, they're pretty good, because they're usually quite small and high capacity, but it would be, again, one of those portable devices and not something you could really use for passive acoustic monitoring. Because one of the things is that microphones weren't actually designed to be left outdoors for a long period in rain and wind. So they're quite sensitive pieces of equipment, which, a lot of reasons, we're now just throwing microphones out and expecting them to do this. When they're being blown on by wind and rained on, which isn't good for them. But as a sort of like carrying it around, if you hear something you want to record it, then smartphone can be quite useful for that.
Sorry, I'm on mute, I didn't realise. Sibby was just asking, can the text from the slide with all your references in, can that be shared around afterwards? I can send that out.
Yeah, sure. I won't put it up now, but I guess in the recording, then people can just pause on it, or if there's anything you were interested in, just drop me a line.
Yeah, bear with me again, there's a lot going on in the chat. Mike's asked, what software do you use for displaying spectrograms? I think that's supposed to say I find Audacity not very good. Cool Edit Pro is better, but need Windows XP. I have some phone apps that are good, but not so convenient to have it on the phone.
Yeah, Audacity is nice because it's free. I've got Audition. I forget where I picked it up, but I've had a copy of. I think you can actually get the old version of Audition for free, because Adobe sort of stopped supporting version. Another one, actually, though, the one I found most useful is Kaleidoscope. Now, you can sign up for I think it's a 1-month trial with Kaleidoscope for free. And after 1 month, they'll switch off the recognizers and the automated ID side, but you still can use the spectrogram viewer. And what's nice about that is you can, if you've got a load of sound files and you want to skip through them quickly, if you're using Audition or Audacity or something like that, you have to open one, then close it, which takes a lot of time when you've got hundreds of them. And when you use the spectrogram viewer within Kaleidoscope, you can just press a button and it skips automatically to the next one in the queue. There's also programs in R which you can use to display spectrograms, but that's quite tricky. And a friend of mine who does bird calls has actually complained, why isn't there a decent spectrogram program around? All the scales look rubbish on the ones that there are and things. There's another one called Spec, S-P-E-K, which does spectrograms. So there's a few choices. You kind of have to shop around and pick the one that best suits your purpose, I think. Yeah, someone's just put up in there that Kaleidoscope has a free live version for you.
Yeah. Someone else also said in the chat for everyone to check out Forest 404 on BBC Sounds app, post-apocalypse drama about the loss of nature sounds with sound recording for each episode. And the second podcast talked about the rainforest example that you used before and after selective logging. Ria's said Chirpomatic is great for bird calls. You can record and ID using the app. Is there anyone else with any more questions? Please put your hand up on Zoom or post it in the chat now. I'm conscious that we're supposed to be finishing in a minute, so get in quickly if you would like to.
Sorry.
No, don't worry. Okay, I think that's it then. Well, thank you very much for joining us today, Rich. It was really interesting.
Thanks.
Especially like the recordings of the reef. I've never heard a coral reef before, so that was really cool. So yeah, thank you everyone for coming today. And hopefully
if anyone wants to contact me about anything that was in there, or a paper, or questions that they didn't get a chance to ask, then that's no problem.
Yeah, I'll send around a follow-up email to everyone afterwards. I'll include Rich's email and then any sort of useful links, etc. as well. So you'll have all that in there. So yeah, thank you everyone, and hopefully we'll see you soon. You can unmute yourself to say bye. I find it really
Bye, thanks.
Thank you.